So I'll continue my lecture from where I left off. And there is one theorem that I stated, which is the following. Theorem. Let mu be an invariant measure. I'll recall what everything means. First, let me write down invariant measure for S sub t. And let x sub tx, right? X member of E be irreducible let's also assume that ST is Strong-Feller. Then unique
Strong-Feller.
Okay, so this is the last theorem that I wanted to say yesterday. And this theorem is due to Doob. So you all know Doob, right? He has the basic martingale inequalities and L2 martingale inequality, upcrossing inequality, Doob's martingale convergence theorem, and so on and so forth. Right? So he is a very prolific mathematician who also worked quite a bit on potential theory and probability, right? Among other things. So here, irreducible, what does it mean? It means you can go from anywhere to anywhere else, right? Almost anywhere else. Positive probability, right? So I'll just recall, that means you choose any little x and any time t and any small open ball if you want to, or any open set, and that would be positive. So I said that this is like approximate controllability, right? You are able to go from anywhere to the vicinity of, to the neighborhood of any other point. What is Strong-Feller? Very good, yeah. Bounded Borel measurable functions are mapped to continuous bounded, right? It transforms bounded Borel to continuous bounded functions. So that means S sub t, if you operate it on B sub b of E, it goes to C sub b of E. That means it smooths it out, right? Okay, what is an invariant measure? Invariant measure means the distribution remains the same, right? That's one way to say. And that's fine. You can just say, I will be off. Then mu is the unique ergodic measure. What is ergodic? You take invariant sets, right? What is an invariant set? ST indicator A has to be indicator A, right? Pointwise or mu almost surely? Mu almost surely. So that's called an invariant set. If mu of A is 0 or 1, then mu is ergodic, correct? So I'm just recalling so that we are all on the same page. Okay, how to prove this? Okay.
We give an intuitive meaning to that last slide.
Yeah. Right. Mu of A is 0 or 1. This is like a 0-1 law, right? And that's why we always get the limit to be a constant and so on, right? If you take, let's say, the strong law of large numbers, then you have the time average, right? You all remember 1 over n times summation xj j varying from 1 to n, right? It converges to some constant. The reason being that it has to be, the limit has to be in the tail sigma field, if you know what tail sigma field is, right? And therefore, those are only constants because it cannot vary between two different values with positive probability, because that would mean that an invariant set can be taking values strictly between 0 and 1, right? That's not allowed. So the limit has to be measurable with respect to the invariant sigma field or the tail sigma field, and therefore the 0-1 law applies there. All right. So that's the idea. And which is why in the Birkhoff ergodic theorem also we got a phase space average, right? Average over the state space, because that would be a constant. Therefore, the eigenfunction corresponding to the eigenvalue 1 would come out to be a constant. Right? These are all needs to be proved, but I'm just stating some. Now the proof. Step 1. There are only 2 steps, so don't be afraid. What it says is these px of p dot, okay? X can be anything in E or equivalent measures. And then here I'll write for all t. You can choose any t and then look at vary the little x's, and they will all come out to be equivalent. This is a technical statement. Okay, so one cannot get enthusiastic about it right now. Yeah. And what is equivalent measure? Do you all know what is equivalence of two measures? Nu. Yeah. If mu is absolutely continuous with respect to nu, nu is absolutely continuous with respect to mu, right? Okay. So, if mu is absolutely continuous with respect to mu, and nu is absolutely continuous with respect to mu, what does that mean? Yeah, I heard you, and I thought I heard something else. Yeah. Okay. So how to say that? Would you then say that this means, right? Mu of a set A is 0, let's say, right? What would that imply? Mu is also, right? That's all you can say here, right? And the corresponding statement with mu and nu reversed holds also. Therefore, maybe that's what you meant by they don't distinguish, right? Okay. All right. So how do we prove this? Let's see. So let me ask you a question. So I take any x naught. Take any x sub 0, member of E. All right. Let B be such that Px0 of Tb is positive. Then to prove the equivalence, it's enough for me to say that if this is so, then for all little x's, Px of Tb should also be greater than 0. Because that would be the contrapositive, right? Here what you said was it doesn't distinguish 0 sets, correct? Therefore, if I have a set with positive probability, the same should hold whether I start with x of 0 or any other x. Correct? So we need to show Px of Tb is greater than 0 for all x, right? Then do you all agree that equivalence would have been shown? Right? So take any x sub 0 such that, so if there is a positive probability under one measure, there has to be positive probability for the other also, right? Okay. So Px0 of, instead of putting a t, what I'm going to do is I'll call it as s plus t. You can always break any given t into 2 parts. Right? Very good. Then what is Px? What is the Chapman-Kolmogorov equation? I can split it, right? It is Px0 of P dy, and then I go from y to where? B. Remember the routing, right? You go from x0 and then you hop over y, whatever y is, because you are integrating over all y, and then you come back to the set B. This is happening in time t units and this is in s, right? So this is the Chapman-Kolmogorov equation. Since this is positive, what can we say there? What can we say about Py of SB? Can it be identically 0? No. So this quantity is positive, right? Because that's what we assumed. Therefore, there exists a y sub 0 such that Py0 of SB is positive. Okay. Therefore, now, how else can I write this? Using S sub t, S sub s. This is the same as indicator B of y sub 0. Agree? What have we assumed about S? S is strong filler. Indicator B, where B is a Borel set, that's Borel measurable. Therefore, this is a continuous function of y sub 0. Therefore, there exists a ball around y sub 0 in which this quantity is going to be greater than 0, right? Therefore, by strong filler, there exists a PR of y0, a ball of radius r, however small it may be, it doesn't matter, such that Py for all y is all okay? And then now we will go to considering what we want to prove, right? Namely Px. Now consider any x and take this. And this would be, once again, you can do the same thing, right? Instead of little x naught, x sub 0, I can take like this, dy. And then what else? Py of SB. Agreed? So I'm not doing anything that you didn't see in the last class, right? I'm just using Chapman-Kolmogorov equation, strong-filler property, right? And once again, Chapman-Kolmogorov equation. But I'm assuming that it is any little x. Okay. This is greater than. I'm not going to do it only over y0. All right? Px of ty, the same thing, okay? You can also write this part again. The same integral, but I'm only integrating over Br of y0. I know that this quantity is positive, right? Therefore, can I say that this is positive? Irreducible. Very good. Yeah, that's right. Because just because the integrand is positive, right, doesn't mean that the integral has to be positive, because it may be over a set of measures 0. But we know that this is going to be Px of t, Br of y0 is positive by irreducibility. That's one condition we haven't used so far. You also want the set over which you integrate to be of positive measure. Okay. So I will just write it down, and that concludes the first step. Okay. And the second is much simpler. So which is positive, right? Since dy of dv sb is positive on Br of y0, and the measure Px of t Br of y0 is positive. This is by irreducibility. And that concludes the proof. All right? Okay, now how does use this to prove step 2? Namely, mu is the unique ergodic measure. All right? Unique ergodic measure. So that's what we want to prove in this step. That's why I'm writing it. So ergodic means we got to consider an invariant set. Let A be an invariant set. Such that mu of A is greater than 0, let's say. We got to prove that mu of A is 1. Correct? Now, now what should I do? So, I can use the definition of invariant measure. So, what is mu of A?
Smaller. What is ST of I is equal to? ST of indicate A is equal to indicate R.
Yeah.
What is the meaning? Because your ST is strong feller, it must land in the bounded continuous functions. That's some contradiction.
ST. Oh, I was defining what are known as invariant sets in this way. How did I define invariant sets? Is this the only way that we defined? You are right. Yeah, because indicator A is there. Indicator A. There is a mu almost surely.
So how do you
Right. And maybe we shouldn't write it this way. Invariant set has to be defined as. How did we define it? Anyone remember? Good question. Strong fellow should smooth it out. And it is mu almost surely, right? So maybe in the almost sure set there is one can do something to smooth it out. Let's see. Supposing you have, let's say, ST of indicator A comes out to be, let's say, integral of indicator A of x, and then the heat kernel, let's say, for instance, right? Let's say k of t, there has to be a y minus x dy, correct? And that of course comes out to be a smooth function, right? So there has to be some convolution that smooths it out, and that's the meaning of it. Yeah.
IA is not C infinity, right?
That's right. No, it doesn't have to be C infinity. Yeah, it is, at least it has to be continuous bounded. That means it picks those sets A for which this is true, and we call them as invariant sets, right? Okay, that's a good. I'll tell you more later. And anyway, in the since there is this these kind of smoothing kernels that are available, something happens. Maybe it should be worded differently. Now, let A be invariant such that mu of A, we need to show that mu of A is 1. That's what we need to show, right? Let me finish the proof and tell you more. Now, mu of A is integral since it's invariant, right? Mu is invariant. So it would be, what would it come out to be? P, I can put in Px of TA, Px of T, Ty, let me call it, right? Mu dy, yeah. This is the definition of invariant measures, correct? So mu of A is positive. Therefore, there has to be mu dy, no, mu dx, okay. That's why, yeah. It has to be the initial measure, right? So it is mu dx. So if this integral is positive, that means therefore there exists some x sub 0. And I had to put an A there, right? Yeah. Therefore, there exists an x0 member of A such that Px0.
Why is A?
Because I'm taking mu of A.
Px of T, A, right?
Px of T. This is so much. This is the entire space. Okay, okay. Very good. Very good. Now I'm happy. Yeah. Therefore, there exists an x0 such that Px0 of Ta is positive. Okay. Now everything is fine. But in step 1, we said that if one of them is greater than 0, all of them are greater than 0, right? Therefore, Px of Ta is greater than 0 for all x. Okay. Very good. And then what do we do? Give me 1 second. So, yeah.
Irreducible means that it is positive for any x, right?
Correct.
So you assume that irreducibility.
Right.
So
I assume.
don't know why you need the first step.
But they need not be equivalent, right?
If they are anyway always positive, so I don't
Right.
see how you need to show that one set is equal to 0 and the other measure is equal to
Yes, right? Given a measure, given a starting point x, you can get to any point, right?
Yeah.
With the probability, with a positive probability.
G is an open set.
Right, G is an open set. Yeah.
Okay.
You
So
cannot
in
say for all.
That's right, not for all, but for all sets.
definition said about irreducibility involves that G is open.
Yeah, yeah.
Oh, I see.
So, just give me 1 second. Something bothers me. We are almost there. So, okay, we need not say that these are just positive. Okay. A is an invariant set such that mu of A is greater than 0. Since mu of A is greater than 0, I can actually pick an x sub 0 member of A actually. Let me once again explain. Let me explain one more time. It's all confusing. We need to show that mu of A is equal to 1. Mu is invariant, right? A mu of A is greater than 0 and mu is an invariant measure. Therefore, there exists an x sub 0 member of A such that Px0 of t, whatever t it is, okay, comma A can actually be made as equal to 1, okay, by using the fact that A is an invariant set. We haven't made use of the fact that A is invariant. Right? So A is invariant means S sub t indicator A is indicator of A, right? Mu almost surely. So if mu of A is greater than 0, then go here and then take some things, right? The right hand side becomes 1 when x is in A. Therefore, definitely there exists an x sub 0. You choose an x sub 0 which is in A, and here also x sub 0. The equality has to hold for some x sub 0. Right? It cannot be different because mu of A is a positive, a set with positive measure. All right. So Px0 of Ta is actually equal to 1. Which would mean by step 1 that all the Px of Ta are equal to 1. Correct? Yeah. All right. So now we come to write what I wrote. Integral is P sub x of Ta mu dx. This is always equal to 1, therefore mu of A is equal to 1. That's all there is to it. It's actually quite simple. And that's what we wanted to show, right? That mu of A is equal to 1. And so it is only here that I use the fact that mu is invariant. Huh? This is from step 1. Yeah. Yeah, because we have ST indicator A to be indicator A, right? And mu of A is a positive set. Therefore, take any little x from A. This equality need not be true only on a null set. But then this is a set with positive measure. Therefore, I can pick an x sub 0 member of A such that Px0 of Ta is 1. Because Px0 of Ta is precisely this left hand side. Right? Yeah. Okay. So mu is ergodic.
So question.
Yeah.
Show it for all x because in the step 1 we showed that if it is positive
For some x, huh? Uh-huh.
positive for all x.
Is that all that we used? For some x, huh? How did we define irreducibility? Irreducibility was defined for all x, correct? Yeah. So I keep up with the same definition. Is that all right?
Px of Ta is positive, but you cannot conclude that it is equal to 1.
Px of Ta. See, I'm having an equality here. See, let me write down here.
Because in your
Indicator A is indicator A, and mu of A is positive. So evaluate both sides for little x's in A. There has to be equality somewhere. Call that as x sub 0. At least one point has to be there. So when you do this, what is the meaning of this? It is precisely P sub t, P sub x0 of TA. And this side, it is going to be 1. That's all there is to it.
Next step. From there to next one.
They are all equivalent measures, right? So step 1, step 1. Therefore, yeah. So that's why I wrote keys.
Right.
So everything is okay. You all understand? So mu is ergodic. Now, how do we show that it is the unique ergodic measure? Well, it is unique because if nu is another invariant measure, then repeating the steps, nu will also be ergodic. Okay. And then what we do is, they are all equivalent. Mu is equivalent to all these px of TA. Okay? Mu is equivalent to px of t for all x. Nu is also equivalent to the same thing. Therefore, mu and nu are equivalent. But we proved that if mu and nu are two distinct ergodic measures, they have to be singular. That was proved in the last class, right? Therefore, mu is equal to nu. That's it. That's Doobe's ergodic theorem. Doobe's theorem on having these sufficient conditions to characterize ergodicity. Right? So very often the invariant sets become trivial, right? Almost trivial. Therefore, no problem about the smoothing and all that. They will all happen to be sets with measure 0 or 1. Now let's get to that's right. That's why that equality makes sense. Meaning, there are very few sets there. That's the idea behind it. Right. Yeah. If S sub t is actually smoothing, that means it won't allow A to be anything other than the full space or empty set, things like that. Right? Okay. So everyone comfortable with this? Yeah. Okay. So
historically, this was in Doobe's book, or it was on a paper?
In a paper, yeah. In transactions, I think. I don't remember. I have it actually, but I'll have to find it. Yeah.
This mu should have some regularity, like outer regularity or something.
Which one? Oh, the measure mu. Good question. Finer properties of the ergodic measure. One has to analyze, what is its support, and is it regular, and so on and so forth, inner regular, outer regular, whatever, right? But then if you just take a single measure, probability measure on a Polish space, it will come out to be regular.
Complete metric space.
Huh?
Complete metric.
Yeah, because it's a complete metric space, right? So that question, good that you raised it, but I'm just saying that that's a theorem. Now, so the main thing to remember here is, first we need an invariant measure. It has to be strong feller and irreducible. Then you can prove that it is ergodic, unique ergodic, right? Because there can even be two separate ergodic measures, right? On two different surfaces or whatever, or subsets. Okay, enough of this measure theory, right? Measure theoretic arguments. But we cannot get completely out of it. But now I'll make you all happy, because now I'll come to evolution equations. All right. You're all happy about that, right? Okay. Yeah, you all know functional analysis, correct? Okay, then you can help me. So we put all this aside. Right? This is Doobe's theorem, and now we can apply Doobe's theorem, right? And first, we'll consider the simplest equation, namely du of t, or du of t plus, let's say, sigma d w of t. All right. Pose these problems on a separable Hilbert space H. Real separable Hilbert space.
That's why you put
Oh, I'll explain what everything means. I have to, right? And let's assume the very basic, namely A is, let's say, A is the generator of a strongly continuous semigroup. A strongly continuous semigroup, S sub t, let's say. All right? That means A is typically an unbounded operator, therefore you cannot define it on the whole space H, right? If I don't define a bounded operator on the whole space H, what can you do? If it is only densely defined, you can extend it, right, to the whole space. But then here it's, as others pointed out, you cannot really afford to define it on the whole space because it doesn't make sense. It's an unbounded operator, and it's the generator. As Professor Adimurthy told you all, it's the Hilly-Yoshida theorem, right? That would tell you, that characterizes the operators that would generate C0 semigroups. So we will assume this. Let's call this as 1. 2, what else do we not know here? Sigma, right? Let's say that sigma is a continuous operator from H to H. I don't want to bring any more spaces, therefore I take the simplest. Continuous linear operator. Okay, and what shall we do with the W? Let's just write, let's say that W is a cylindrical Wiener process. That is given a complete orthonormal system E sub j H. Given a cylinder, okay, we can represent, right, W sub t to be, you can expand it, right? Bj of t, where Bj are one-dimensional Wiener processes, independent, one-dimensional, a bunch of copies of independent Brownian motions or Wiener process, however you call it. They are all standard one-dimensional Wiener processes. You all know this, right? It cannot be really H-valued. Why? Because it is going in all directions like a Brownian motion, right? There is nothing to dampen it, right? Therefore, this is not H-valued. That's why we call it as a cylindrical Wiener process. For instance, if you think that it is actually h valued Wiener process, take the norm, right? Then according to this, it will just become bj squared of t. Okay? Because ej's are complete orthonormal, and therefore if you take the expectation, its variance is, you can interchange the summation and the expectation sign because everything is positive, right? And it becomes infinity, right? So it's a useless process because it is becoming, the variance is becoming infinity. But that's not really the only reason. You can have processes which have variance to be infinity. But if you take, let's say, do you all know what is known as the characteristic function? It is just a close cousin of the Laplace, Fourier transform, right? In probability theory. So take the Fourier transform, it won't come out to be, it will just become 0.
That's equal to which one?
And the expectation is the variance becomes infinity. Does it make sense?
Pardon? Yeah, that's right. So actually, that's what I'm trying to say here, that we don't get Wt to be an h because the norm squared comes out to be infinity. Right. So that was my point, that it is not really h valued Wiener process.
So where does it lie?
Yeah, it will lie in a bigger space. If you want to give a meaning to this, h is there, consider a Banach space such that this is a Hilbert-Schmidt embedding, and that would automatically put weights when you compute the norms, expectation of norm squared, right? The norm squared.
So it will become an eigenvalue power.
Then there will be a lambda j also multiplying it, which is convergent and so on.
Oh, that is where the inverse.
Right, that's right. That's where the Hilbert-Schmidt embedding comes in.
Yeah.
So these are all ideas that go back to Sazonov, Minlaws and Sazonov. Minlaws actually considered in the Hilbert space setup, and Sazonov proved it in the space of distributions and so on. He went to the biggest space and then proved a dual of a nuclear space and stuff like that. So the test functions were too small, and one could actually construct whatever. You're laughing.
Why? Because that was a continuation of our breakfast talk.
Right, yes.
Okay.
So there are various setups. You can either work in the given space or go to a bigger space and then make everything to be really Banach valued. Okay, so let us just work with this. So under this, if sigma is just a continuous linear operator, this sigma dw has no meaning, right? Because if you take sigma to be the identity, let's say, then you are left with a Wiener process, and that's not h valued. Okay. So nonetheless, we'll go ahead and write down what the solution is, and a mild solution. So it will be e to the t x plus integral 0 to t. E to the t minus s a sigma dw. That's the mild solution. Okay, so I'm writing certain things that do not have meaning. So I had to put some more conditions. I want to show what those conditions are. So let's consider this part. I would like it to be an h. So the integral of sigma dw itself need not make sense, but maybe with the action of the semigroup it may make sense. That's the normal way. So what is this? Let's put in one more condition here so that everything makes sense. And now dw is summation of bj, ej, right? So I can write this as dbj of t and then ej. Are you all following? So I'm just calling this as the mild solution, right? then you can actually show that the mild solution is a weak solution and so on and so forth. Because these are very simple equations, right? I haven't exactly pinned down what A is though. So the EJ can be brought inside. So shall I do that here itself? EJ. So that's what the integral is. Where is this integral? Yeah, if I call this integral as I, that's I can be given this representation. J's are coming, so I had to have a summation sign. Or you can adopt like 3, the summation is there. Well, maybe I'll put the summation sign since I think you guys were discussing, right? There is a summation sign. Okay. All right. So let's now compute what this is. If you want to, you can even break it down further. I can know qualms about it. If you do you all want to write it like this? T minus S A sigma EJ EK times EK EQJ of T. Maybe that will make some of you happy, but then there are double integral, double summation. Let's say that we do all this. Then you can sum it up in this way, but first with respect to K, maybe the K can be outside. Let me just, and then write the same things. If I'm doing the summation, then this EK can even be put here, right? Here there was EK, I can bring it outside. Okay. So I have some quantity. All these quantities are here. This one is there. The EK alone, I took it there. Now let's take the expectation.
Sorry.
Yeah. Oh, I just interchanged them. The integral is still there. Huh?
You have one summation.
Sigma acting on EK
Right.
Sigma is
operator, and
It's
EK
an
is a
operator.
basis function, and so therefore you want to expand that.
That's right. I thought that if everything is, I'm just trying to make it easier, but maybe it's a little clumsier. I don't know.
sorry, different question. What properties has sigma?
What properties?
Is sigma?
Sigma is just a continuous linear operator right now. All right. Now let's take the norm form. Can anyone tell me what happens? I have some real value quantity here, right? My purpose was everything is now made real. I should put this here. Here. Yeah. So this is the inner product, and that's a real value. This is also a real valued process. So everything is real here multiplied by EK. Therefore, it's a Hilbert space. So I can write it as summation over K. And then the rest is with respect to Vj. So now I'm taking an expectation as well, and then S squared. You understand? I can even keep the expectation for now here. It doesn't matter. Everything gets squared, right? The whole quantity that I had there gets squared. That's all it is. And then what happens? It's a dBj integral, right? The summation and integral can also be exchanged as it should be, and therefore it will all become expected value summation over k, summation over j of e to the tk, t minus sa, sigma ej ek squared ds, right? Integral is there. and expectation is gone. I took the expectation and so on. So all I did was what? Plancherel's theorem, right?
Right.
And then made use of the fact that if you integrate anything, f dv, let's say, you square it and then take the expectation. It is the integral of x squared dx.
To isometry.
Yeah, e to isometry. Have you all heard of e to isometry? That's very basic, right? If you- Pardon? Oh, I see. Very good, very good. So that's all that I did. Yeah.
The battery has gone.
Oh, yeah. And then bring the k inside and the j outside. So it is just you all understand what happened here? And if you take the summation also inside, then it is integral 0 to t. The summation is precisely what's called e to the t minus s a sigma squared in the Gilbert-Schmidt norm, right? I hope it's all understandable. You just work it out, right? I made it into two summations and an integral. You just do Plancherel's theorem a couple of times, and then the e to isometry that I written here, then this is what you get. And this same thing can be written as, what is this part? It is another name for this summation, okay? You take the summation of whatever is inside and call it as Gilbert-Schmidt norm squared. And this is e to the t minus s a sigma right. Once again, we write it in a slightly expanded form, and then you can write it as the trace. That's all I'm trying to tell you. So then, this quantity becomes actually the integral 0 to t. You bring this maybe to the other side, correct? By putting the transpose, it all becomes, what does it all become? Transpose sigma star e to the t minus s a sigma e to the t minus t minus s a sigma ej comma ej. And there is, of course, a summation that I'm missing. I had to put back the summation. And this can be identified with the trace. That's all. This quantity is called the trace. You can even put the star here, right? So you can even write it in this way. Sigma star. First write it as the trace of this, and then you can exchange them. All right? We'll call this, then the trace can be taken out, and whatever remains, we'll call it as trace of q sub t. So that defines what q sub t is, where q sub t is the following operator. Trace of, not trace, integral 0 to t, e to the t minus s, a sigma star, e to the t minus s a star ds. Right. So if this expected value of the norm of I squared, I mean, if it has got to be finite, what do we want? We want this trace of qt to be finite, right? thus norm of I squared is the same as trace of Qt. Let us assume that Qt is finite. Trace of Qt is finite. Those are called trace class operators, right? For all t. Okay. So that is Qt is an operator of trace class, is a trace class operator. Let's write like this. Okay. Probably you all knew this from Professor Rudier's lectures, right? You would have seen these kind of integrals and maybe even harder ones. And I was just patiently describing to you by expanding it into. Oh, okay. But you would have seen these summations, whatever it may be. And or it all comes with an isometry. Yeah.
One comment might help is that if you take sigma equal to I, then,
that's right.
this is immediately finite because A is negative Laplacian.
If it is, yeah, right. The usual.
Yeah.
Yeah.
This is finite.
Correct.
On the other hand, if you go to the original equation and try to do energy
Right.
by variational methods, it fails because you have trace of Q, right? Yeah, that's infinity.
Correct.
So in this way, the mild solution is superior for the linear problem.
Yeah. Right. Very good. Maybe I'll write it down. So you all understood what Professor Sridharan mentioned just now. I'll, like I said, that this is an assumption for all t, right? Greater than 0. Now let's look at some examples because this is kind of. Then it would drive home the truth about all this. So let's say that your space is H is L2 or 0 pi, and sigma is just the identity operator, and A is just AF is, let's say, dx squared of F with a minus sign.
The way you formulated is minus.
Yeah, minus sign. Well, I didn't say it's a dissipative operator, but you're right. Yeah, we can take it to be so. That's the nice part. Yeah. So AF is minus dx squared. That means I'm doing it in one dimension, right? So I don't have to write Laplacian and all that. Then do you all know the domain of A? This was mentioned by, several times. It's a subset of H. H is the L2 function, so it doesn't have derivatives in the usual sense. So you go to the weak sense. And you know that this is H2. And then what? I'll also say that I'll assume that I'm looking at the Dirichlet prediction. So I'm looking at the Laplacian operator with boundary conditions to be 0, let's say, right? And using resolvents and so on, what did we learn? It allows you to use the spectral theorem. And therefore, there exists a complete orthonormal system of eigenfunctions, right? And what are these? Lambda j squared, j squared. You all know? J squared times Ej. Correct. This can be easily scratched and found out, right? When I write down what Ej is, you would all know. Some constant times. What is the constant? 2 over 5 to a half or something? Times sine Jx, right? So you can actually find out, differentiate sine Jx once with respect to x, you get a j cos Jx. Then differentiate it one more time, you would get another j, right? And then our operator has another minus sign. Derivative sign is cosine, derivative cosine is minus sign. Minus or minus becomes plus. So you get j squared. So no big deal. So Ej, right? It's a complete orthonormal system. And what else should I say? Let's look at this e to the t minus s. A, e to the t minus. So it's A is a self-adjoint operator. And what is Qt? So sigma is just identity. So sigma and sigma star are gone. A and A star are the same. So you can say e to the 2 times t minus s. ds. What is its trace? You got to do the EJ business, right? So I'll put a summation over j, e to the 2 times t minus s. A acting on EJ, we know is j squared, right? I want a negative sign. Where do I have the negative sign?
e to the power minus
Minus, right? Minus sign is there. And then what else? What have I done here? I have acted an EJ, right? Pardon? And then ds is there. You all understand? Because there is a j squared and then EJ is 1 because it's normalized. Okay, so what does this come out to be? Integral 0 to t. When you expand it and so on, 1 minus e to the minus 2t j squared is there, huh? Something divided by j squared, right? 2j squared or something like that. Okay, this is what you will get, I think. Okay. So it is on the order of 1 over j squared and therefore it's finite. You know that summation of 1 over j squared, j varying from 1 to infinity is finite. But if you go to 2 dimensions, it won't be so, right? So if you go to some L2 of 0 pi to the n or something like that, right? Where n is greater than 1. Is that okay?
Yes.
Yeah.
Actually, I spoiled you. AF is you originally right. It's just without a negative. And therefore, the A of EJ,
right? Yeah,
I
yeah,
can
yeah.
use minus j squared.
Minus j squared, yeah.
And everything else.
Yeah, that's what I thought, yeah. Right. We always like positive operators, so you put a minus sign there. Yeah. And L2 of 0 pi to the n. Then you can once again consider this as h. I'm not going to work out the whole thing because time is flying, right? And sigma is I, let's say. Calculate trace of Qt, right? Show that trace of Qt is inside. All you need to do is, if you are summing up 1 over, now you need multi-indices, right? So trace of Qt, identify it with something like over J1, J2, Jn. So there are n summations here, and you will have J1 squared plus Jn squared. And that won't be summable, right? And therefore you need some help from sigma. And it is precisely, right? If you take, if sigma is taken to be minus a to some power alpha, then that would help us. And find alpha such that trace Q is finite. Again, you can expand everything in terms of j squared and so on, and therefore you'll get alpha to be greater than n over 2 minus 1 or something like that. All right? I'll leave this. We can think about the tutorial if you cannot get it. Okay. So now let's go with the main things that we have to be doing, right? What was this talk about? It was not about solvability, right? Because I cannot do solvability as well as invariant measures. We identified that we need three things. One is there has to be an invariant measure. And then we had to show Strongfellow property and what else? Irreducibility. So three things. So three things in 20 minutes, okay. I'll prove the minimal. So first statement, let's say proposition. Now, we wrote a mild solution, right? And there is also a semigroup for that process. The semigroup is how do we define S sub t? Phi. S sub t phi of x, right? That would be simply expected value of phi of u. Right. That is, your initial point is little x, and you are finding the expected value of this solution at time t. That's a semigroup. That's called the Ornstein-Uhlenbeck semigroup. Why? Because what I described to you, the equation that I wrote is called the Ornstein-Uhlenbeck process. Okay. S sub t is Strongfellow, provided u sub t h u sub t to the half h. Let me see what the condition is. It's actually quite. When I work out, I will get it. But then, since I put it out there, let me give you a condition for it. U to the TAH has spaces, okay? E to the TAH has to be contained in QT to the half H. Proof. Okay, first of all, I have to say that our solution has a good distribution. So I will write it in the proof here. What is the distribution of UTS? It is just perturbed by a Brownian motion, therefore it has to be normal, right? But it is in the infinite dimensional sense, right? So UTX is Gaussian. If you don't want to call it as normal, you can say it is Gaussian. So if you look at our solution, it was e to the TAX plus integral 0 to t, e to the t minus s times a, sigma d w of x. Correct? This part is called the stochastic convolution. Stochastic convolution integral. And then here is something else that is appended to it. That's just a constant, right? Because I took little x to be a member of H. Therefore, Okay, this is a stochastic integral, so you can show that expectation is 0. That's nothing, because you can make it all once again into real valued Brownian integrals, and therefore it's 0, so it's just e to the TA x. And what is the variance? We just now computed. And the variance operator, I'll just call it as QT. The trace came in when you had to put the absolute value and so on, right? So it is an operator, it's a trace class operator, and we call it as Q sub T. So let's call the is this distribution. We'll call this distribution measure, right? There is always the normal density is there, then the normal density corresponds to a distribution on the real space, and we can call it as mu or something, right? So distribution is always on the state space. I'll just call it as mu x. You all with me? Now d mu xt. So mu, when x is 0, I'll call it as mu of 0t, obviously. So the very first denotes something about the expected value. I left off the e to the ta because otherwise it'll look clumsy. And the time is actually listed here. The variance is qt, that's understood. When I put t, that means the variance. It stands for the variance being q sub t. Now, what do you think this is? This is actually this is a distribution, this is another distribution. Here let's say that the mean is x, here it is 0. Right? So before we compute this, let's go to one-dimensional case and I'll tell you what happens. Right? So supposing you have, let's say, a normal random variable with mean m, let's say, and variance. Variance is not variance is important. Variance is, what shall I call it? D squared. Well, D is not such a good name. Beta squared or something. Okay. Then you know how its density looks like. Correct? It is going to be 1 over square root of 2 pi. You should help. Beta comes there. And then what is there here? X minus m squared divided by 2 beta squared, right? Correct? Okay, so I have this density. That corresponds to this, let's say. Just for a second. Instead of t, I have beta squared, right? That's all right. And then I'm going to divide by, instead of m, I'm going to take it to be 0, right? X squared. Of course, I'm going to later on, yeah, I'll worry about other things later. So this is correct. So instead of the little x, I made it as m. Does that bother anybody? It shouldn't. I want to evaluate at y. If you want to, I can call this as y, so that I don't make wholesale changes. Okay. Now, what cancels? Several things cancel, right? This cancels, and this will cancel with part of this. So what remains? Let's write it on this side. E to the minus what? Minus m squared, okay. Divided by 2 beta squared. And then what else? Plus 2my divided by 2. So 2's can my divided by beta squared, no? Excellent. So what happens in the infinite dimensional cases, you view this as e to the minus 1 over 2. M squared over beta squared is there. Let's write it as m beta m beta. It looks silly. I had to put beta inverse, right? I can put it in any order that I want to in the one-dimensional case, all right? Maybe I would like to put it as beta inverse m. Beta inverse m is multiplied to beta inverse m, and therefore that's the very first part. And how can I write the other part? Plus m divided by beta, so I can write it as beta inverse m, right? And then I have y over beta, that is beta inverse y. Okay, I'm writing, okay. These are all now understood, so I will erase these. So there is some space. Beta inverse y, okay. That's exactly what I need to write here as well. But it's not so simple, okay? This is called the Girsanov transformation. Girsanov transformation is about translation in the infinite dimensional space, which means there has to be a Jacobian. It is the Jacobian that I'm trying to write here. That's not an easy task, even in the case of, right? If you want to rigorously prove Girsanov theorem, it will take a couple of classes, 2 or 3 classes. So let me write down here what we found. This is the lesson that was learned in the one-dimensional case, or in finite dimensions for that matter. If you know finite dimensional multivariate normal distribution, the same thing will happen, right? Except that beta inverse has to be the inverse of a matrix, correct? It will be a matrix sigma, which is called the variance covariance matrix, and its inverse will be there. Okay, yeah, to the half, because beta squared was our variance. You got to first take the positive square root of it, right? And then write it to the power. So everything will be to the power half. Here it is all everything to the power 1, because I took the variance to be beta squared. Okay, so what would I get here? Let's see. Instead of m, what do I have? E to the tx, e to the tax, and then qt is my beta squared. So qt to the minus half, e to the ta x. You all understand? And then I got to write the same thing, right? Okay. I'll complete this. And then what else? Qt to the minus half. Instead of m, I had to put e to the tax. And then what is beta inverse y? Qt to the minus half y. You understand? Does it make always sense? I had to make sure that e to the tax is in the range of q to the half, right? Which is why I needed all these kind of conditions, right? E to the ta, and then I pick any little x, right? Which was taken to be our initial condition. E to the that has to lie in qt to the half h. The qt to the half h is what is known as the Cameron-Martin space, right? And actually, the normal distribution doesn't charge this Cameron-Martin space. Measure is 0. But only in those directions can we translate. All right? And so what I have done here is the Girsanov transformation, right? Girsanov theorem, or Cameron-Martin theorem. All right. So having done that, what shall we do? St of pi. Now we are almost there. It's there, right? Just phi of y, let's say. If you start at y, that's how it happens, right? No, that's okay. X is actually nicer. I'm sorry. Here also I'll put STX. I had to compute this integral, right? What is it? It is the integral phi. I'll call this as y. The values of u of t of x I'm calling as y, all right? And then what should I integrate with? It has to be the distribution of u t x, which is this, right? In other words, I called it as mu xt dy. You all understand? This is how we find expectations, right? Expectation of a random variable means you integrate the values of the variable times the probabilities. Here, the values of the variable times the density function, right? Okay, let's take a breather. What is it we are wanting to show? The theorem says that ST is strong filler, right? Which means what? I got to show some continuity with respect to x. But where is x? Unfortunately, it's the lower subscript of a measure. I don't like it. So what I'll do is, I will divide by mu 0 t dy, and then put a mu 0 t dy. Do we know this? That's what we computed just now. And that's all explicitly in terms of x. And therefore, I can actually show the continuity with respect to x. That's the idea. Therefore, this would become integral of phi of y. Let me just write down one statement at least. And then let's call this, it's too long, let me call it as L sub t. Just a notation. Plus LTX qt to the minus half 1 mu 0t dy. How would you show continuity? I had to show that as xn converges to x, st phi of xn converges to st phi of x, right? That's a strong Feller property. So you should be able to take the limit somehow inside. Is LT a continuous operator? You all said, you know, functional analysis. And I'll give you a hint though, that's not very fair. Use this and closed graph theorem. What is closed graph theorem? You have to go and search for it, right? This exact statement. So using closed graph theorem and that condition, you can show that LT is actually a continuous operator. All right? So if it is a continuous operator, then everything is uniformly integrable and so on. When you take x to be in a bounded ball, there is nothing that goes wrong. First of all, this part can be taken out, right? E to the minus 1/2 LTX, that can be taken outside the integral. And this is like some constant times y. That's integrable with respect to the Gaussian measure with variance q sub t. All right? I have shown how to do this in my notes. I have actually done an overkill, I think. But that's all right. Overkill is better than underkill. And by dominated convergence theorem, take the limit as x goes to 0. All right? LT is continuous. It's a continuous operator. By closed graph theorem. This part can be actually taken outside. Let me just call it like this. That waits outside. Phi is actually bounded, right? Okay, phi of y. And then you have to worry only about this part. So you can write it like this if you want to. And then use, if you got two numbers a, b, you can make it as less than or equal to a squared plus b squared with constants, right? So you can actually write this, give more constant here and less here, and that would be enough. because there is in here there is a e to the minus 1/2 qt to the half y waiting for you, right? That's one way. So mu 0 t dy, then we can pass to the limit. We can take given a sequence xn such that xn converges to x. This quantity, we can take limit. We can show that S of t phi of xn converges to S of t phi of x as n goes to infinity. That's precisely Strongfellow condition, right? And just quickly, in a minute or two, I started 5 minutes late, right? I won't take all 5 because everyone is hungry, right? And I'll just take, so that I don't have to talk about linear equations later on. Yeah.
Why do you substitute the scalar product with the product of the models in the last line?
Oh, I was just saying that you have. I know. I'll tell you. Because if you are given a sequence xn, you can always bound it by a constant c, right? And therefore, by continuity, LTX will also remain bounded, right? And therefore, if I make use of the fact that AB is less than a squared plus, let's say, epsilon b squared I want, so this will become 2 over epsilon, right? Then identifying A with this part, I can bound it all by a constant, because if all the xn's are bounded by some constant, LTX will also be bounded by a constant in absolute, in norm, right? And therefore I can actually take it out. Maybe I should have put a norm, maybe that's, right? Okay, that's probably what confused you. And then I just can bound whatever I have by a constant times something that depends on little x and so on. I'll just have e to the epsilon times the square of qt to the half y squared, which is integrable with respect to mu 0 t. So irrespective of what n is, everything is bounded by an integrable function, and therefore dominated convergence theorem applies, right? I was going a little bit quickly there. I'm just sketching the proof here because it's all there in the notes. Okay, so another proposition. Why is it irreducible, right? So we got to prove that S sub x dx is irreducible. Prove. Take any x, number of h, and take any ball, right? And be R of. That is an R ball. And you should be able to go from x to B or Z. We can take without loss of generality that Z is 0. To simplify matters, right? Take Z to be 0. Okay, so we had to now compute the probability that in a given time, right, u of tx comes to the R ball, right, is less than R squared, let's say. We got to show that this is positive. That's all there is to it. So here is the ball, radius R, and you might have started somewhere here. And we had to compute that you can come in here given any time t. Choose any time t. T is just greater than fix any time. And we got to show that this is positive. Right? Okay. Now u of tx These are all normal variables, right? So you can expand it in the eigenfunction E sub j, right? You can write it as, okay, first in order to not write too much, I can write this as mu xt of norm y squared less than r squared. See, you can write everything in terms of probability on the original probability measure or come to the representation space, right, in computing probabilities. So this is the distribution. So I come to the values. Now, what is norm y squared? It is summation of yj squared. J varying from 1 to infinity, right? So what is yj? It is the Fourier expansion, right? Y comma ej. Got it? And this is exactly Parseval's theorem. Now, what kind of a random variable is y sub j? These are all independent. Y sub j are independent normal variables with some alpha j, let's call it. I'll define what is alpha j. And then what will I have here? Lambda j. Because I'm taking the eigenfunctions which form a complete orthonormal system, and we know that the variances are given by trace of qt, right? Therefore, I just get them to be lambda j. Is that all I get? Is it lambda j or lambda j times t? It doesn't matter. You can always take t to be 1, then what I wrote is correct. Or independent normal alpha j. What is alpha j? We are almost done. E to the ta x, right? Comma ej. That's all it is. So these are all real valued normal variables. Okay. So you can say that this is greater than or equal to mu xt. So here I'm following a trick by D'Aprato. Okay, D'Aprato, what he does is simply makes it all into very easily digestible parts. Maybe the first 10 terms have to be less than r squared over 2, and the next ones have also got to be less than or equal to r squared over 2, so that when you put them together, it will all be less than r squared. Yj squared r squared over 2. Here j goes from n plus 1 to infinity. Why are they independent? I told you that they are independent, right? Which is why the probability measure split up. So these n variables are independent of these. So I can split them up. All right. How many of you think that this part is positive measure? If you are summing up n independent random variables, you again get a normal variable, so you again get a normal variable. Normal variable has support everywhere, right? So it has positive probability, however small r may be. That's easy. How about this part? Well, call this set as A, right? Then what you can do is mu xt of A complement, consider that. Then that means it's greater than r squared over 2, right? And then apply yj squared from